Hi, here we are with part 3 of 4 parts of our final topic in Advanced Topics in Math for spring of 2020. Is we are trying to figure out how to find large prime numbers. Okay, so in the last video, I introduced the Euler criterion. We proved that and saw how that works. And in this video, what I'm going to do is introduce 3 new things: the Legendre symbol, the Jacobi symbol, and the law of quadratic reciprocity. And once we have those 3 things, in the next video, part 4, I will outline the Solovay-Strassen algorithm, which uses uses the Euler criterion, and then what it does is it uses the quick ways, uses quadratic reciprocity, so we can quickly compute the Legendre and Jacobi symbols, and then we can fairly quickly get to with reasonable probability whether we understand if a number is prime or not. So that's our goal. 3 things here today: the Legendre symbol, the Jacobi symbol, and the law of quadratic reciprocity. Okay, so big ideas here. The law of quadratic reciprocity is something that is fundamental in number theory, and it was conjectured by Euler and Legendre, and it was proved by Gauss. So we're going to slowly develop those ideas here. Okay, first thing, the Legendre symbol. So this is just a symbol that we use to indicate whether something is a quadratic residue or not. So it looks like this, Legendre symbol. Okay, so P will be an odd prime. And then for any integer P, for any integer A, we have this symbol here. It looks like this. We write it this way. That is the Legendre symbol. It's A over B, where A over P, where P is prime, and that symbol it will equate to 0 if A is congruent to 0 mod P. This is unimportant. Okay, as you saw before, we're often excluding the values of A which are evenly divisible by the prime. Okay, and then then the other 2 cases is that the Legendre symbol will be equal to 1 if A is a quadratic residue, and it will be equal to it is defined to be equal to -1 if A is not a quadratic residue. So there are precisely 3 values for the symbol: 0, -1, and 1. And these 2, the -1 and 1, are the ones that we're really going to be interested in. These are the important ones. Okay. We saw from before then, we in fact know how to calculate if A is a quadratic residue mod P, and that was this way here, A to the P minus 1 over 2 mod P, and we knew that if it's going to be a quadratic residue, that has to be congruent to 1. So I mean, that is in fact the same as the Legendre symbol. So the Legendre symbol comes out to be 1 when this congruence is 1, and -1 when the congruence is well, it comes out to be -1 when the congruence is -1. Okay, so we're going to get, first I'm going to just give a quick example, but we're going to see actually how to calculate these things a little bit differently. So here's an example. We could ask, what is the value of the Legendre symbol when A is 133 and the prime is 1597? Okay, so the way we could do that is by modular exponentiation. We could just go like this: 133 to the 1597 minus 1 divided by 2 and mod 1597, and you do that calculation and you find out that it is 1. That tells you that, well, it tells you the Legendre symbol is 1, and it also tells you that A is indeed a quadratic residue mod, well, 133 is a quadratic residue mod 1597. Okay, so this is again the modular exponentiation. We are going to try to, in fact, avoid doing this and see if we can develop a way even faster of doing this. Exponentiation. Okay. All right. So before making this calculation, you of course can only do this if this is prime. So if you saw a calculation like this, you should check that this is prime. Okay, because it needs to be prime. Okay, so that is what the Legendre symbol is. Okay, next thing, so that's a definition. The next thing we'll do is define the Jacobi symbol. Define the Jacobi symbol. In this case, n will be a positive odd integer. And I will write n in its prime factorization. The product from I equals 1 to k of the ith prime raised to some exponent. Okay, for example, let n be equal to 9975. Then I would factor that, and I would get 3 times 5 squared times 7 times 19. So this would be here P1 with an E1 equals to 1. So P1 is 3 and E1 is equal to 1. And here P2 is 5 and E2 is 2. And P3 is 7 with E3 equal to 1. And the last one, P4, would be 19 and E4 is 1. So that's how I'm representing I'm representing n. Okay, and then I will let a be an integer. Okay, and then I use the same notation, but in this case, n is not prime. If n was prime, then this would be a Legendre symbol. Here, this thing in the bottom, the denominator, if you will, is not prime. That's the difference. And so how do I calculate the Jacobi symbol? I do that as the product of the Legendre symbols in this manner. Okay, let us identify what k is in a second. So here, this is going to be a over pi to the ei. Okay, where this thing here, because the denominator there is prime, this thing here is the Legendre symbol. Okay, and the k, the indexing, the k there, that is how many distinct primes I have in n. So this is the number of distinct primes in n. In the fact, let me even be a bit more specific. In the factorization of n. So in my example here, you could see that there's 4 prime numbers here. So in this case here, k would be equal to 4. So I would calculate 4 Legendre symbols. I would raise the Legendre symbols to these exponents. And then I would form the product, and I would get the Jacobi symbol. Okay, so let us just write out at least some numbers as an example here. So let us take a look at, for example, computing the Jacobi symbol of 6278 and 9975. Okay, so I would then write this in this manner here. I've already factored it, so it would look like this, 6, 2, 7, 8, and then that's the first prime there, 3, and that's the first power EI, which is just 1, so you don't really actually need that there, but just for clarity, that is there. And then we would do the next prime, 6, 2, 7, 8, and that is 5, and that we would square because of E2 in our calculation up here, E2. E2 is 2, so that is squared there. And then we get the next prime, which is 7, 6, 2, 7, 8, 7, and then 6, 2, 7, 8 over 19. Okay, so we would need to calculate all of those Legendre symbols, which each one of which is going to be most likely to be 1 or -1. If one of them is 0, of course, then the whole thing goes to 0. But so long as none of these primes are evenly divisible into the 6, 2, 7, 8, then all of these will be plus or minus 1, and then the result will be plus or minus 1. Okay, so there's a few things here that we don't want to have to do, and really what we don't want to have to do in particular is factor. We've the whole thing about RSA, in fact, being secure is that it's difficult to factor large numbers, and we want to avoid that at all costs. And what we had to do here in this calculation, so far anyways, is we, in the way of finding a Jacobi symbol from the definition, we had to factor 9975 into its prime factors, and that could be a time-consuming proposition. So I'm going to first now introduce now the law of quadratic reciprocity, and then we'll come back to this calculation and indicate a bunch of different properties of the Legendre and the Jacobi symbol that we can use to compute them without factoring, because that's really what we want to do. So I'm gonna, in order to do that without factoring, we need the law of quadratic reciprocity. So here it comes, a major result in number theory. Law of quadratic Okay, so a couple things. We're going to have two primes, P and Q. So we'll have P and Q. Let P and Q be distinct primes. Excuse me. Okay, and I'm going to introduce another idea here, and I'm going to say this of the form 4k plus 3. It is in fact the case that you can take every prime number and represent it in one of two forms. It'll either be of the form 4k plus 1 or 4k plus 3. I'll show you what that means in a second, but right now let me just get this law down. So P and Q are going to be distinct primes of the form 4k plus 3. Then one of x squared congruent to P mod Q and x squared congruent to Q mod P is solvable. And one is not. Okay, let's just pause here for a sec. Actually, I'm going to get the rest of the definition out, and then we're going to go through it carefully, making sure we can understand what this is saying. But if at least one of the primes is of the form 4k plus 1, then both congruences are solvable, or both are not. Okay, there's a statement of the law of quadratic reciprocity. Okay, so let's take a careful look at a whole bunch of things here. One is an important thing here is to take a look at the two congruences that we're talking about. We're talking about x squared congruent to p mod q, and we're talking about x squared congruent to q mod p. So in this one over here, if this congruence here were to be solvable, that would mean that p is a quadratic residue mod q. And that actually tells you, depending on the form of the primes, whether or not q is a quadratic residue mod p. Okay, so one of them, they're related in this, I think would possibly not be an intuitive thing to think of. So they're related in this manner. So if p is a quadratic residue mod q, then, and the primes are of this form, then q is not a quadratic residue mod p. Okay, but on the other hand, if we have a different form of a prime number, and we find out that p is a quadratic residue mod q, then we know that q is also a quadratic residue mod p. Okay, so that is actually telling you in terms of the Legendre symbol that this fact is true. This is an immediate consequence of this statement. Let me write it down, that the Legendre symbol PQ multiplied by the Legendre symbol QP is minus 1 to the P minus 1 over 2 times Q minus 1 over 2. That's a consequence right there. Okay, so let us take a look at a couple of examples here, because what we're going to do is use the law of quadratic reciprocity in order to find the Jacobi symbol without factoring. That's our goal here, because factoring is slow. Okay, so let us first take a look at the types of primes. Let us just look at a few primes and what type they are. Okay, so let us just look at the first few small prime numbers. Let me just take a look at, say, p is equal to 3. That's a prime number. And then I write it in this form like this. 4 times 0 plus 3. That is equal to 3. So this prime number, p equals 3, is of the form 4k plus 3 with k equals to 0. Okay, let's take a look at another prime number, 5. P is equal to 5. So we think, what does that look like? Well, that'll be 4 times 1. 4 times 1 is 4, plus 1 is 5. So that's equal to 5. So this is of the form 4k plus 1 with k equals to 1. Let's keep going. With next prime number, p is equal to 7. 7 looks like this, 4 times 1 plus 3. That's 7. So the prime p equals 7 is of the form 4k plus 3 with k equals to 1. I'm just going to do some more. I just really want to emphasize this point to you. Let's see, 8 is not prime, 9 is not prime, 10 is not prime. Oh, 11 is prime. Let's take a look at 11. So I'm thinking, okay, let me divide out as many 4s as I can. So that would be 2 of them. 4 times 2 plus 3. That's 8 plus 3. That's 11. So 11 is of the form 4k plus 3 with k is equal to 2. Okay, and let's just keep going. Let's take a look at 13. 13, I could go 4 times 3, that's 12, plus 1. That is 13. And so that is 4k plus 1 with k equals to 3. Okay, this is, in my opinion, a remarkable fact in itself that we haven't spoken about before, that every single prime number can be represented as either 4k plus 1 or 4k plus 3, where k is some integer, some positive integer. So we can divide the primes into two types, the 4k plus 1 type and the 4k plus 3 type. Okay, so what I highly encourage you to do, first of all, to just, marvel at this remarkable situation. Go through some more primes. So go through, 10 more prime numbers. And make this calculation and see for yourself that you're going to be able to find them to be all of them to be like this. Okay, so that is what is referring up here in the law of quadratic reciprocity. If P and Q are distinct, that means different, primes of the form 4k plus 3, so that in our example down here would be this one, or this one. That's 4k plus 3. And then if I can solve x squared congruent to P mod Q, then I will not be able to solve uh, x squared is congruent to Q mod P. Okay, but then here, if I'm on the second statement here, if one of the primes, at least one of the primes is of the 4k plus 1, so if one of the prime numbers happen to be 5, for example, then I will be able to solve both of the there's two possibilities. I'll be able to solve both of the congruences, or I'll be able to solve neither of the two congruences. So that's what this law is telling us. We are not going to prove this, unfortunately. Okay, let's take a look at some examples. Let P equal 3 and Q equal 5. Okay, so we're now thinking about two congruences. X squared is congruent to 3 mod 5, and we are thinking of the second congruence, x squared congruent to 5 mod 3. So you see what's happening here. That is, the P and the Q's are reversed. They're sort of reciprocals, if you would. It's not really true, but they're, you've reversed these two things here in order to get this one over here. Okay, these two congruences are related in that manner. Okay, now we take a look at what type of primes we have. Well, we already figured out that this one here is of type 4k plus 3, and this one here is of type 4k plus 1. Okay, so as soon as I know that, I now know via the law of quadratic reciprocity that of these two equations, there is two possibilities, both solvable or neither solvable. So that's just based on this knowledge right here. So I haven't solved either of these congruences, but I know that if I solve one, I'll be able to solve the other, and I'll know if I can't solve one, I won't be able to solve the other one. I mean, that immediately halves the amount of work. If you actually wanted to solve, well, it certainly halves both the work if you found out one's not solvable, because you don't have to waste time trying to solve the other one either. Okay, so if they're both solvable or neither solvable. That is, I am being told this by the law of quadratic reciprocity. Okay, so now let's actually look at the solution of this. We'll look at x squared congruent to 3 mod 5. So I'm asking, is there some number in Z5 where if I square it, the residue will be 3? Okay, so I could just going to go through on brute force. You could use the Euler criterion, but we're just going to go through here on brute force. 5 is small, so I can easily just take a look at all of the numbers. So if we say, I wonder, what is 0 squared? Well, 0 squared is 0, so that clearly doesn't work. I take a look at 1 squared. 1 squared is 1. That doesn't work. I take a look at 2 squared, and 2 squared is 4. And then I take a look at 3 squared. 3 squared is 9. 9 mod 5 is 4. And then I take a look at 4 squared. 4 squared is 16. 16 mod 5 is 1. So I didn't get a remainder of 3 on any of those. So I'm looking at the residue when I square the numbers in Z5. None of those residues turned out to be this number 3. So there is no solution. So this congruence here, x squared congruent to 3 mod 5, has no solution. Okay, now I could ask exactly the same thing of the second congruence, the related congruence, x squared congruent to 5 mod 3. I could go through the same procedure to try to determine whether it had a solution or not, but I don't have to. So I immediately from quadratic reciprocity, no solution. Okay, that is via quadratic reciprocity. I do not have to make any calculations, but let us just make the calculations so that we can assure ourselves that that is at least correct in this case. So I'm going to say, can I square something that is congruent to 5 mod 3? Well, 5 mod 3 is 2. So let us just take the numbers in Z3. So now I'm taking a look at the numbers in Z3. That is 0, 1, and 2. Okay, and then I'm going to square them. So I will 0 squared will be 0 mod 3, 1 squared will be 1 mod 3, and 2 squared will be 4, which is also 1 mod 3. Okay, and then 5 mod 3 is 2. So none of these numbers here, these ones here, are 2. So this one's also not solvable. I already knew that because of the law of quadratic reciprocity. Okay, we're going to take another example. Let's have let P equal 3 and Q equal 7. Okay, so now what I'm doing is considering the congruences, the related congruences that are like this: x squared congruent to 3 mod 7 and x squared congruent to 7 mod 3. Okay, I'm then going to look at the form of the primes. I have already identified 3 to be of form 4k plus 3, and 7, let's just look back in our table, we've identified 7 to be of the form 4k plus 3 as well. Okay, so both of them, both primes are of the form 4k plus 3. Okay, so let's just wind back to the law of quadratic reciprocity. Let P and Q be distinct primes of the form 4k plus 3. So we're in the first statement of this law. They're both of type 4k plus 3. Then one of them is solvable and the other one is not. So immediately I know when I'm looking at these two related congruences here, via the law of quadratic reciprocity, I know that I'm going to be able to solve one and I'm not going to be able to solve the other. So will be able to solve one and not the other. That is what I now know. Okay, I don't know the solution to either one of them, but I do know that if I can solve one, I won't be able to solve the other one. So let's just take a look at one of them, and then we can draw the conclusion about the other one. So I don't know, the working, let's just think, working mod 3 is faster because we only have 3 numbers to check. So let me check this one, x squared congruent to 7 mod 3. Okay, if I'm going to do a brute force look at this, I mean Z3 only has those 3 numbers, so I can quickly check. We already in fact did this. 0 squared is 0, 1 squared is 1, and 2 squared is 1. Because 2 squared is 4, and then mod 3, that is 1. And then what is 7 mod 3? 7 mod 3 is 1. Okay, so that means that one is solvable. Okay, so I in fact found the solution. X squared congruent to 7 mod 3 has a solution. And that solution is, which one is, in fact, it has 2 solutions. The solutions are 1 and 2. Has a solution, has in fact, let's do this properly, 2 solutions. And that those are x equals 1 and x equals 2. And furthermore, those are negatives of one another. For example, 1 is equal to minus 2 mod 3. Okay, that's what we saw when we were proving the Euler criterion in the last lecture. Okay, so it has two solutions, and there they are, and they are negatives of one another. Okay, now what do I know? I now know I've solved that one. So then I look and I now know, with no further calculations, I now know that this congruence, x squared congruent to 3 mod 7, is not solvable. Okay, don't have to do anything to do that, but just because this whole thing is new, I am actually going to look and see whether it's solvable by brute force. I expect it to be not solvable, and if I do somehow solve it, then I've got an error somewhere. So let's just take a look in Z7. So in Z7 we have the numbers 0, 1, 2, 3, 4, 5, 6. So I want to just point out one thing here. When you know that one's going to be solvable and the other one is not, clearly trying to solve one of them, it's smart to pick, and if you're going to just do it by a exhaustive search, it's smart to pick the smaller number here when you start. Okay, especially if you're writing an exam, you want to sort of do it the efficient way. Okay, so we're going to check this. So I'm going to square all of these numbers mod 7. So 1 squared is 1, 2 squared is 4, 3 squared is, I'll just do it like this. 3 squared is 9, and 9 mod 7 is 2. Okay, then 4 squared is 16. 16 mod 7 is 2. 5 squared is 25. 25 mod 7 is 4. Okay, one more to do. 6 squared. 6 squared is 36. 36 mod 7 is 1. Okay, so I've now checked all of the possibilities that there are, and none of those numbers are 3. Okay, so I see that it's indeed not solvable, which is what I expected to have happen. So none of these numbers here are 3. So there is no x such that x squared will be congruent to 3 mod 7. Indeed, I've checked, and I already knew it was not solvable via the theorem of quadratic reciprocity. Okay, so now that we've got the idea of the Legendre symbol, the Jacobi symbol, and the law of quadratic reciprocity, I'm going to list some facts, sorry, that we can use to get around, so we can get around factoring. What we want to be able to do is calculate the Jacobi symbol without factoring, because that is time-consuming and very difficult, particularly with large numbers. Okay, so that's our next thing here. Okay, that is going to be, I'll even put it in this way. Properties of, properties, I'm going to even state it sort of rather colloquially, properties to get around factoring. Okay. Property 1. M1 over n is equal to M2 over n. So the Jacobi symbol for M1 is equal to the Jacobi symbol for M2 if M1 is congruent to M2 mod n. Okay, okay, let us just make a statement here. N will be odd and positive. N is odd and positive. Okay, we're never going to be checking even numbers to see if they're prime. Okay, so we're always thinking here of n as being odd and positive. Okay, I'll just make a note of that. Even numbers are never prime, except for 2, and we've excluded that in this whole theory. Even numbers are not never prime. Okay, all right, so we're here. This feature is that If M1 and M2 are congruent mod n, then they have the same Jacobi symbol. That is a feature that we call periodic. Okay, that's basically we're moving from one equivalence class to the next equivalence class. So for example, if we're working mod 7, 2 and 9 are the same, and then we can keep going like that. Those numbers all have the same Jacobi symbol. Okay, property number 2. 2, the Jacobi symbol for 2 over n is equal to -1 if n is congruent to plus or minus 1 mod 8, and is congruent to is equal to -1 if n is congruent to plus or minus 3 mod 8. If n odd. Okay. Property number 3 of this symbol, m1 times m2 over n is equal to m1 over n times m2 over n. That property is what the Jacobi symbol is a multiplicative function. Okay. Final property. If m and n are odd, then m over n is equal to the minus of n over m, and it's equal to n over m. This is if m congruent to n congruent to 3 mod 4, and this is otherwise. Okay, what am I actually writing down here? This is a fancy way of writing something we have just been talking about. Think about this here. This statement right here, this important property of the Jacobi symbol, it's going to make it much easier for us to calculate this thing. This property right here, this is another statement right here of quadratic reciprocity. So take a moment right now, maybe stop the video, write that down, and then wind back and look at the statement of quadratic reciprocity and see if you can see how this is an equivalent statement. It is. Okay, so now let us take a look at first calculating a Legendre symbol without doing quite as much work, and then we're going to do a longer example computing a Jacobi symbol without doing any factoring. You'll recall when I did the Jacobi symbol, let's just wind back here so I can show you what it is I'm trying to avoid in case that's been lost. When I calculated this Jacobi symbol here, I factored. I factored this 9975 into its prime factors, and I used all those in order to make the calculation. That is what I'm trying to avoid, and I'm going to be using quadratic reciprocity and potentially some of these other features here in order to compute these symbols efficiently. Okay, so we're going to go for an example here. We're going to try to calculate this Legendre symbol here, 133. We already did this, in fact, and we already have, in fact, a formula for doing that. We did it. Okay, so this is an example, and we've already done this, but that is, I calculated it with the modular exponentiation. Now I'm going to look, can I do this another way that is less time consuming? Mod. We did it this way, 1597, and that's equal to 1. Okay, so we know the answer. The answer is 1. Okay, so first of all, we're going to notice a few things. That is that 1597 is an odd prime. Okay, we'll notice that the GCD of 133 and 1597 is equal to 1. Okay, so now I'm going to start to go on how to calculate this thing in a different manner using the rules. Okay, first thing is I'm going to factor the numerator. I'm not factoring the big number, the potentially bigger number of the denominator. I'm going to factor the numerator. I'm going to factor 133 into 7 and 19. Well, I can't factor the denominator, actually it's prime. Okay, factoring the numerator. Okay, why can I do that? That's because of the multiplicative factor. So this is true because the Legendre symbol is multiplicative. Okay. Then I'm going to take a look at 7 and 19. What kind of primes are those? Because I'm thinking I'm going to be using the quadratic reciprocity. So I'm thinking what kind of primes are 7 and 19? So I notice that 7 is equal to 4 times 1 plus 3. And so that is of the 4k plus 3 flavor. And then I look at 19 and I see that that is of the flavor 4 times 4 plus 3. So that is of the style also 4k plus 3. And I take a look at the 1597 and I see what kind of prime is that? Well, that's 4 times 399 plus 1. And so that is of the form 4k plus 1. Okay. So I have I've turned the problem of finding the Legendre symbol for this into the product of two Legendre symbols. Now I've looked at the types of the primes, and now I'm going to be thinking first of this first Legendre symbol. So right now I'm wanting to find this Legendre symbol. Okay, both of the 7 and okay. Oh no, hang on a sec. 7 is of this type, 4k plus 3, and 1597 is of this type, 4k plus 1. That means by the law of quadratic reciprocity, both of them are solvable or both of them are not solvable. Right? So now I'm thinking of these two congruences. I am thinking of this x squared congruent to 7 mod 1597 and x squared congruent to 1597 mod 7. Okay, those are the two congruences, and I know because of the forms of the prime, either both of those are solvable or both of them are not solvable. That's what the law of quadratic reciprocity is telling me. Now, when I think about this, what is the Legendre symbol when a number, in this case 7, is a quadratic residue? The Legendre symbol is 1. So if I consider this product here, okay, this is 7 a quadratic residue mod 1597 multiplied by the answer is 1597 a quadratic residue mod 7. That's what that is. Now they're either both solvable or they're both not solvable. That means the Legendre symbols are either both 1 or both minus 1. That means that the product is 1 because 1 times 1 is 1 and 1 minus 1 times minus 1 is 1. Okay, so I know something about the product of the two Legendre symbols. Okay, this is actually going somewhere. It's actually getting easier. Okay, similarly, let's look at this product of two Legendre symbols. Is 19 a quadratic residue mod 1597? And is 1597 a quadratic residue mod 19? Well, similarly, because this one is of type 4k plus 1, this one is of type 4k plus 3, the answer is either both yes, or the answer is either both no. Either way, the product of the two of them is 1. Okay, so that allows me to do this. So now, first step, I use the fact that the Legendre symbol is multiplicative. Second step here, I'm using quadratic residue. Okay, now I'm going to rewrite my problem, which is this Legendre symbol times this Legendre symbol. Okay, because this product is 1, I can replace this right here, 1597, with 7. And I can replace this one, 1597, with 19. That will not change the result. Okay, then I can use the periodicity property of the Legendre symbol, and I can simply take 1597 mod 7, and I get 1. And I take 1597 mod 19, and I also get 1. So now my problem of finding the original Legendre symbol, this one here, is boiled down to finding the Legendre symbol here. Okay, so this step right here is I think that was, let's take a look back. Yeah, that was property 1, right? Right there. The Legendre symbol is periodic. Okay, so that is the periodic property right there. Okay, now I can easily figure out that the Legendre symbol is 1 quadratic residue mod 7. Yes, it is, because 1 squared is congruent to 1. I mean, that's mod 7. I mean, similarly, this Legendre symbol is also 1 because 1 squared is congruent to 1 mod 19. Okay, so I then can conclude from this without having, well, okay, I can now conclude from this that my original question, this Legendre symbol, is equal to 1. And that is in fact what we found out before by doing this much more time-consuming calculation. So we did a large modular exponentiation. We found out the answer was 1. And then instead of doing that, I started the same problem again, and I used a few properties. I used the property that the Legendre symbol was multiplicative. Then I used quadratic reciprocity. Then I used the periodic property, and I got the same answer, and I did not have to do a large modular exponentiation. Okay, we're going to do a final example before I conclude this video. We are going to calculate a Jacobi symbol without factoring. And this is going to be the key thing for how the Solovay-Strassen algorithm works. Okay, it needs to go through, it needs to calculate the Jacobi symbol and then draw a conclusion on whether something is prime or not based upon that, and give a probabilistic answer. And so this is the key feature for having this algorithm work quickly without having to factor. Okay, so our objective here is compute the Jacobi symbol, this one here, 7411 over 9283. There it is. Okay, I take a look at this is going to be minus. I'm going to flip it upside down, but you notice that minus sign is coming there. 2837411. Why? That is by property 4 by 4 quadratic reciprocity. That's because I can look at the types of the numbers and figure out that 1 is solvable and 1 is not solvable. So I can flip it, but I need to put the minus sign in this case. Okay, take a look at the numbers carefully while we're going through this. All right, so then now I'm almost always going to do this. I'm going to reduce mod 7411. I'm always going to use the periodicity property to make the numbers smaller when I can. So that's what I'm doing here. 7411. There. That is by 1. These are the facts that I gave you about the Jacobi symbol. So this one here is the periodicity. Okay, so I keep going. I now factor 1872, and I factor that into 2 to the 4 times 117. Okay, so this is going to be 2 to the 7. Okay, so here it is. 1872 is 2 to the 4 times 117. Okay, so that is 7411 to the 4 then, and then here I have 117 over 7411. Okay, that is by 3, property 3, the multiplicative property. Okay, and then I had that property. Let me just wheel it back and show you what it is. It's property 2. Let's see here, this one here. So now I'm going to invoke this property 2. I have the number 2 over something, 2 over n, and I'm looking, is n congruent to plus or minus 1 mod 8, or is n congruent to plus or minus 3 mod 8? Okay, so I'm going to use property 2, and I'm going to find out that it's 1. Okay, so that is going to be right here. This thing here is going to evaluate to 1, so it just kind of, it disappears, if you will. So this thing here is by property 2. This thing is evaluating to 1 by property 2. So that's by property 2. Okay, so that leaves me with a simpler situation here. That is going to then be, let's move this down slightly. That is going to be 117. The minus is still there. 117 over 7411. That is by that coming from, I'm coming from property 2, eliminating that piece right there. Okay, now I am going to reverse it, and I'm not putting in a minus sign here. So I want you to go through this example and understand, when I reversed it this time, I did not put in a minus sign, but so there's those two cases in quadratic reciprocity. Either the product of the two of them is going to be 1, or the product of the two of them is going to be minus 1. So this is by property 4, quadratic reciprocity. Okay, then I can reduce, like I'm always going to do when I see this. That is, I'm going to take 7411 mod 117. I get this here. That is by property 1. It's periodic. Okay, then I factor 40, and I get this minus 2 over 5. So 40 factors into 2 cubed times 5. And then that's by 3. That's the multiplicative property. Okay, and then I have that situation here. I have 2 over 117, and that is minus 1. And then minus 1 cubed is minus 1. So I'm just going to do this again in red because I did the last property 2 in red. So now I'm looking at this thing right here, and this is equal to minus 1 by property 2. Okay, and minus 1 cubed is minus 1. And then minus 1 times minus 1 is 1. Of course, you can see the disaster here. You're going to get one of two answers, 1 or minus 1. So if you make a sign mistake anywhere along the line, you get completely the opposite conclusion that you wanted to come up with. So you have to be extra careful. Okay, so this one here is like that. That was by property 2 going through there. And then I'm going to do the same thing, 117 over 5, like that. And that's going to be by property 4, quadratic reciprocity. And then I'm going to reduce. And that is by 1, the periodic nature of the symbol. Okay, and then I don't know, you could do this fairly easily, even now by brute force, or we could say this is minus 1 by property 2. Okay, so now I've evaluated the Jacobi symbol for well, let me just write it down here at the bottom. I've evaluated this Jacobi symbol, 7411 over 9283, and I've figured out that it's -1. Okay, I did that, and I did not factor this number in the bottom. That's the key feature. So I've did not factor this. Okay, that is what that is what we're going to use. Our ability to evaluate this symbol without factoring that, using the law of quadratic reciprocity as well as those other properties that I've shown here, and that will allow us to develop the algorithm. That'll be the final piece in our RSA encryption thing, and that will be the final video. Actually, this part 4 will be coming up, showing how to use this feature in the Solovay-Strassen algorithm. See you next time. Thank you.